Welcome to the second lecture of the 7th week of the course in machine learning. So this lecture will be about the second theme for this week, which I've called Interdisciplinary Inspiration. Essentially, this lecture doesn't present so much new material. It merely collects together all the parts that have occurred during the course where other disciplines have inspired the work and development in machine learning in particular, but also in artificial intelligence in general. Let's start with what is most important. So, artificial intelligence and machine learning are very much dependent on mathematics and statistics. I hope that this message has gone through. I mean, in this course, I have tried to be on a level that not all the time borrow down into these areas. But I've also said clearly and consistently that when you develop your knowledge in this area, when you go deeper, and when you continue, if you continue with this area after this course, you will, under all circumstances, need to handle much more mathematics and much more statistics. So let's start with mathematics. So there are a variety of parts of mathematics that come into play. So, I mean, one important area is the vectors, matrices, linear mappings, with the inner and outer products for those, measures of similarity in such spaces, how you can differentiate matrices and vectors. Chain rule is an important element in certain corner of machine learning. Inverses of matrices, least square techniques, eigenvalues, tensors, etc. But also geometrical aspects are important. So geometric interpretations of mappings, other things like hypercube, discriminant functions, and so on. And also optimization techniques. Furthermore, graphs and digraphs. I guess you have observed that graphs occurs in various corners also. So in a similar fashion, statistics is also a cornerstone for this area. Statistics are traditionally dealt with data collection, data modeling, data analysis, data interpretation, and data presentation. Maybe we haven't really highlighted data collection and data presentation so much in machine learning. But of course, when you do a practical project, it will be eventually there. Everybody has to collect data. It doesn't matter whether you come from a background where you call yourself statistician, or you come from a background where you call yourself a machine learning scientist. So the core theoretical parts of statistics are, of course, fundamental. Mathematical statistics based on probability theory. So all the fundamentals there are important. In general, machine learning is more dependent on inferential statistics, in the sense that it's statistics which want to draw conclusions on whole populations from the studies of samples, while something called descriptive statistics primarily summarizes the samples themselves and do not draw further conclusions. So specific areas that have occurred during the course are Markov processes, kind of stochastic processes, Bayesian methods, Monte Carlo methods, and so on. So the influence of mathematics and statistics is not, I wouldn't call it just an inspiration. I will call it necessary foundations for the area. Let's move on now to some other disciplines. First, looking at theoretical philosophy and logic. So obviously the classical modes of reasoning inherited from theoretical philosophy and logic have had a strong impact on artificial intelligence in general and machine learning in particular. And those four, the classical ones, deduction, obviously very important in inductive logic programming. Induction is a foundation and general source of inspiration for most parts of machine learning. Abduction as a basis for explanation-based learning and backward reasoning in Bayesian networks. And analogy finally as a basis for case-based reasoning and associative memories. So hopefully you already seen these couplings during the course. The couplings between logic theorem proving and certain parts of artificial intelligence are also very strong. Specific examples that has been mentioned during the course are the following. So early programs in artificial, like the logic theorist program by Newell and Simon, proven theorems from Principia Mathematica. McCullough-Pitts, when they analyzed the capability of neurons for performing logical operations, was based on a specific logic notation used by a logician named Carnap. And logic program is based on a specific theory proving technique called SLD resolution. Finally, Lisp language is based on a variant of a kind of logic calculus, which is called the lambda calculus. So one can continue to count on that. There are many techniques in these areas. There is a source of inspiration in logic somewhere. Let's turn now to linguistics. Probably you will find it more difficult to see the real coupling to what we talked about this course on with respect to linguistics, but I want to say a few words about this discipline. So actually, many aspects of language, including learning of language, is central to artificial intelligence, and the latter for machine learning. And actually, the theoretical and structural view of language had its major proponent in Noam Chomsky, who publishes classical works in tactical structures in 1957. And as you remember, artificial intelligence was defined in 1956. So this view of linguistics, a very formal theoretical view of linguistics, went very well in hand with the developments in computer science and artificial intelligence during the same period. It also was well aligned with the movement away from behaviorism and towards cognitivism in psychology, which we'll come to in a minute. So finally, other linguists like George Lakoff widened the work of Chomsky, not only focusing primarily on syntax, but also on semantics, and also highlighting the importance of cultural differences and embodiment. The various approaches in machine learning reflects a long ongoing debate in psychology, where the pendulum in the last century has swung between reductionism and cognitivism. So reductionism strives for reducing explanation of all mental behavior into neurophysiological low-level processes. So you can easily relate here to artificial neural network approaches in machine learning. While cognitivism are represented by psychologists like Miller, Broadbent, Cherry, and Bruner, argue for the relevance and existence of an abstract model of cognition in terms of symbols, concepts, and logically related inferences. And hopefully you can also easily see there the analogy or relation to symbolic machine learning approaches. So this is clearly the sub-symbolic side of the coin and the symbolic side of the coin. So if one look at psychology during the last 100 years, the pendulum, as I said, has swung between these extremes, and in between them there are various middle standpoints. So if we start with structuralism, which was a very strong movement to beginning of the 19th century. So actually there, in that approach, you try to define the simplest components of our mind, and then put the pieces together to model more complex phenomena of the mind. But in this approach, it's not very empirical. Actually, the evidence was primarily based on introspection, on questions to people and their own reflections on their own thinking and about self-reports. So as a reaction to that came functionalism, which was more looking at the functionality of behavior. So try to explain the processes of the mind in terms of the usefulness of the manifestation of the behavior. Less theoretical, more practical and more purposeful. So that then developed into something more extreme, which is kind of well-known sub-area of psychology called behaviorism, where researchers like Watson, Skinner, Thorndike, Pavlov assumes that all behaviors are either reflexes produced by a response to certain stimuli or a consequence of that individual's history, including especially reinforcement and punishment in certain situations, together with the individual's current motivational states and controlling stimuli. So the parallel to the perspectives in reinforcement learning is kind of obvious here. Finally, things changed again, so we move now more towards cognitivism. So Gestalt psychology is also a part of psychology, which is more focused on the global phenomena in the mind, the holistic parts. And you will see now when we come to neuroscience that also neuroscience has this very complex debate between researchers looking at atomic phenomena or more holistic phenomena. So let's now look at an area which we have touched many times during the course, and that's categorization, or if you want, classification or concept formation. And actually, I think it's fair to say that the inspiration for how we think about categorization comes from not only one other discipline, but from several. It comes from philosophy, psychology, and anthropology combined. So what I want to stress here is kind of two views on categorization. So one view, which I call here the classical view of categories. This has very old roots from Aristotle and the Greek philosophers, but also exemplified by work by later philosophers and psychologists like Bruner. Actually, the idea here, the main ideas are the following. So the idea is categories are arbitrary. So typically the viewpoint is that we as humans define the categories we want, primarily based on our language, our culture, the context we are in. So there is no underlying restrictions that we naturally have to follow. Also that categories have defining attributes, the features we talked about during the course, and the feature value combinations. What defines? It's certainly the feature value combinations that distinguish a category from another. And all members of a category share these attributes, and no non-members share them. So there are no overlap between members of a category and the non-members of a category. So they are. So the intention, which is the set of attributes, actually in a descriptive form, determines the extension. Exactly. This means that they define exactly which these members can be, the members of the category can be. So the member space has no internal structure. It just have a abstract definition, and all members are regarded as equal and first-class citizens of this of each category. And also the levels in a hierarchy, or may not be a hierarchy, it may be a lattice, also have the same status. So the one level is not different from another in such a structure. So as you see, this is a very well-defined, crisp way of defining categories. So actually, the alternative, which we'll call the modern or natural view of categories, or sometimes it's called prototype theory. You will understand why in a minute. So categories here are in many cases motivated by properties of our sensory system and the world surrounding us. So actually in this approach, you recognize that there may be, not always, there could still be cases for objects where the categories can be defined more in an arbitrary way as in the classical. But in many cases, it may be so that there are these restrictions, physical restrictions of our world and our sensory systems of ourselves that actually constrain what is reasonable to do when we categorize. Actually, then, the view here is that one build categories around so-called central members or prototypes, defined by sharing, by that they share more attributes with each other members than with non-members. So therefore, the membership are kind of graded based on this kind of typicality. And obviously, typicality generates a topology of this member space. And the borders between categories therefore are fuzzy rather than crisp, as in the classical case. Also, in this view, the levels in an hierarchy, or lattice, can have different status, where some researchers argue that the middle layers of the hierarchies, which are more correspond to everyday things, called the basic level, while the more abstract categories and the more detailed levels, here called superordinate and superordinate levels, have other properties. So the shift from the classical view to the modern view was kind of triggered by a number of work, and actually a lot of these works were based on a very popular topic. It's actually when people looked at color terms. Color terms, what kind of colors do we fancy to use and perceive in different cultures? And actually, there's a famous study by a researcher named Berlin, where he looked at color terms in 98 countries. So actually, every culture have different views on this. So if you look back at the course, I hope you can see the coupling here, so that you can see that some of the learning methods we looked at are still very much influenced by the classical view, while some others, like the instance-based learning approach, some forms of the clustering analysis, like the k-means approach, for example, are very much inspired by the modern view. So hopefully this explains, it's a very natural coupling. I mean, these are the two major ways of viewing categories, and they are naturally reflected then also in the machine learning methodologies. So let's turn now to neuroscience, an area which has obviously influenced machine learning a lot. So the objects of study are the nervous systems of animals in general and humans in particular. Special focus is also on the brain, and as we have talked a lot about the atoms of the nerves are neurons, Um, and an observation here, of course, that's important, that in the nervous system, everything is analog, not digital, as in the artificial systems we create. So I wouldn't repeat the terminology. We have a terminology here about the parts and aspects of the neuron. What I focus here now actually are two major questions discussed in neuroscience and psychology for almost a century. So one issue is that the belief that brain functions contributing to specific behaviors are primarily local, limited brain areas, which is called the principle of locality. Contra the belief that large portions of the brain contribute to all kinds of behaviors, which is often called holism. The second issue here is the belief that cognitive models of behavior are just a figment of our imagination, and that all that exists is the myriad of atomic neuron activities, which is then termed reductionism. And different people have had different standpoint also with respect to whether everything there is the low-level thing, and it's not meaningful to try to model something on a higher level. So the above two big questions will be further elaborated now, whereby Anna will look in more detail on the work by a number of famous neuroscience researchers. I will talk about Karl Lashley, I will talk about Donald Hebb, I will talk about David Hubel, Torsten, Wiesel, and I will talk about a few other researchers. I want to start by saying a few words about the work by Karl Lashley. So Karl Lashley was one of the most influential neuroscientists of the first part of the 20th century. He started as a student of the father of behaviorism, but developed into the most clear-sighted proponent for a balanced view between holism and localization. So furthermore, Lashley, in spite of being a scrupulous experimentalist, seriously questioned the more extreme beliefs in reductionism. He moved the focus from a mostly passive view of the brain, primarily triggered by external stimulus. So essentially the idea before that was that the brain kind of sleeps and it only do something when it's triggered. While Lashley promoted a view where you have an almost always active brain. Doesn't matter whether you have external stimuli or not. The brain is always active, and it's have a central control and a hierarchical control that proactively accommodate to external input. So essentially, the view here is that you have the brain is active, and it has a central control organization that can then handle and react to the various input that takes place. So there are a few very important concepts that was introduced by Lashley. And one of them is equipotentiality. And by that, he meant that large areas of the brain potentially has the possibility to contribute to specific behaviors. In many of the experiments done by Lashley and others at that time, actually people looked at brain injuries and even artificially caused lesions of the brain. Obviously then studying what was the behavioral effect of that at a certain point in the brain deliberately was damaged or was damaged from some natural causes. So this means that if a part of the brain had a problem or was damaged, then obviously according to the hypothesis of equipotentiality, others areas could potentially take over that not from the beginning had been the major contributions to the behavior. He also introduced this idea about mass action, which has had a related meaning, meaning that the consequence of a brain damage is more proportional, rather proportional to the amount of damage than exactly where the damage took place. And finally, he introduced the idea of plasticity. And plasticity then means that if one part of the brain is damaged, then other parts then can gradually take over the contribution, then making the individual able to evoke the same behavior as earlier, before the damage occurred. So Lashley also seriously researched the possibilities for sharply localizing the manifestation of singular concepts or memories in the brain. And this then relates then to actually the reflection on whether it's meaningful to talk about where a specific memory resides, or exactly which phenomena in the brain correspond to a specific symbol or concept. And he called this endeavor, this search, the search for the engram. And one could say that his conclusion was kind of empirically negative. His conclusion was that essentially it was very fruitless to find this exact evidence, as fruitless as the search for the Holy Grail. And that typically, and the reason for that typically any functionality seems to be spread over many areas. But the way he expressed this in all his writing was merely as temporary negative observations from the research he did. Didn't make any very radical standpoint what theoretically could be possible. So this means that other researchers who really want to find the engram, researchers like Simon and Hubel, they were rather encouraged by reading Lashley than the opposite. So let's turn to the work of Donald Hebb. I hope you remember him. In 1949, he published this theory claiming that an increase in synaptic efficacy arises from a presynaptic cell's repeated and persistent stimulation of a postsynaptic cell. So this Hebb's theory, Hebb's rule, Hebb's postulate, whatever you want to call it, summarized as cells that fire together, wire together. The more they fire together, the more they get connected. And essentially, one can say then there are two ways this can move. So if two neurons on either side of a synapse are activated synchronously, then the weight of that connection should be increased. But if they are not activated synchronously, then the weight of that connection should be decreased. So as Hebb described the overall learning phenomenon of the brain, it was actually a combination. I mean, you can think that Hebb's theory is only local, and of course it is. So Hebb's rule actually describes what happened in each point. So the local learning enabled are directly related to Hebb's law. But also, Hebb in his writing emphasized more holistic learning in the sense that when this, I mean, what happens in a neuron was not a single neuron, it could happen to all neurons in parallel, actually. So if one considered what happened in the whole system, in his view, what was built up was that serial structures or more complex structures were formed. So as a whole, when reading Hebb's, the picture you get is both the focus of what's happened locally, but also how the brain develops more holistically. So the next pair of researchers that we have mentioned during the course are David Hubel and Torsten Wiesel. And actually, during the 1950s and 60s, they did experiments that showed actually that specific neurons in the visual cortexes of the cat and monkeys individually responded to what happened in special regions of the visual field. So these smaller regions of the whole visual field, they called receptive fields, and what happened in the receptive field then primarily triggered locally specific neurons. But of course, it's not these receptives will overlap, so they are not fully separate. So this whole process of responses of specific neurons to set subsets of stimuli within these fields, they refer to as neural tuning. They also hypothesized that there are two kinds of neurons. There are those that handle simpler phenomena in the visual field, like things like corners, geometrical things, and these neurons that can detect this kind of simpler phenomena, they call simpler cells, while there were also other neurons that could react to more complex phenomena occurring in the visual field. And they also hypothesized the model where for a whole pattern or image recognition task, there need to be some model how this is cascaded, where these kinds of cells work together in a more or less hierarchical fashions. And actually, their work is then one of those examples that focus again more towards the locality, obviously. So here is just included one of the slides that we showed earlier when we talked about image recognition. Actually, the current model, more or less, of the human visual system. And I think the main message here is that people believe at this point that we have a pretty clear model of this subsystem. Finally, I want to mention more briefly some other important work in neuroscience that also to some extent influenced the way we design artificial systems of the same kind. So, and also researchers that have different standpoints or contributions in regarding the two questions I raised initially. So Roger Sperry is a researcher that is famous for his work on the two brain hemispheres. Actually, first one to very clearly observe that the two brain hemispheres have different functionality, while the left and right are different. The left have stronger role for language, conceptual oriented tasks, while the right are more focused on spatial functions, as an example. And Sperry also studied then plasticity phenomena because it's not entirely true that the one side of the brain takes care of everything for a specific functionality. So even here, there can be some plasticity. So even if the left is better on language, to some extent, the right also contribute to language issues. And if brain damage occur in one or the other, there can be some plasticity also. But still, there is domination for one or the other. So some Russian researchers, Alexander Luris and others, looked also then into the hierarchical organization, how different brain regions, um, which were which regions were dominating for a certain kind of task and which were more, I would can say, subcontractors. And also, what they try to study is how this kind of role play between the areas would change over time. So, for example, for a child, there could be a certain role play. Typically, when you are younger, more sensory regions dominate over others, while when you get older, the more planning-oriented regions get an upper hand. So essentially, one can say the governance of our thinking change over time in this way. Other researchers looked, for example, at the relation between simple neuron functions and the functionality of the whole organism. And I would say the trick here was that the researchers who were did a lot of contributions on this, they were clever and chose to study very simple organisms. I mean, if you study the humans and more advanced animals, uh, it's so very complex. So if you really want to see the relation between a few neurons and a whole system, then it makes sense to study very simple organisms, which they did. Others looked even more on the localization. So that's another example then related to what we saw in vision. So, for example, there are some famous studies of the song of birds, where obviously the ability for singing in a particular way seems to be very localized in birds' nervous system. So finally, also a kind of famous standpoint that was put forward by a researcher called Karl Pribram is this an analogy between the brain and a hologram. So one can say this is the extreme holistic view, that in the same sense as a hologram being an image recording, where every little piece of the recording can be used to reconstruct the whole image. In the same sense, every part of the brain contribute to everything. But I assume you already understood that this is probably not true. There is some balance here between localization and holism. One look at the sum of all the contributions I have taken. So finally, something related to neuroscience, but actually also related to logic, is the work that has been mentioned, that is considered the starting point of artificial neural networks. That's the work by Warren McCulloch and Walter Pitts. But actually, when that work was done, it was not considered computer science, it was not considered artificial intelligence. It was considered that the neuroscience researcher worked together with a logician, and what they tried to prove was that the architecture, the way they thought the neurons in the brain worked, could function as an architecture for something that could realize or implement logical operators. So this still fits as a source of inspiration, because when this was published in 1943, neither machine learning or artificial intelligence existed, and even computer science was an embryo at that time. So a few things that have been also mentioned, let's not forget them. Everything is not inspiration for neuro science. We also saw that there are some systems we built inspired by genetics and evolution theory. So evolutionary computing in general and genetic algorithms in particular are inspired by Darwinian ideas about evolution and the survival of the fittest. So in these models, one used these terms. You look at populations, so you can read a data set is a population. You have chromosomes, which is more like a data item, where every position in the chromosome corresponds to a gene. Read the same thing as feature. And continuing that, this kind of systems are try to mimic the way one can see evolution works. So you have generations of populations, and in every cycle they are evaluated with respect to how fit they are by using some fitness function, and the fittest subsets are allowed to reproduce, and reproduction takes place either by something called crossover or something kind of mutation, and there is a certain order of these phases. So even genetics and evolution theory has to some extent inspired work in machine learning. I want to end this lecture by mentioning some inspiration not only from cognitive sciences but also from physics and engineering science, and I hope you will have some recollections when I go through them. So, for example, there are some inspiration from thermodynamics. So, for example, if you remember the information gain measure that we talked about in context of building up this decision tree, one used an entropy measure as the basis for the information gain, and actually an entropy measure over the probability of a class membership. And this is, of course, strongly influenced by the concept of entropy in thermodynamics. And actually, entropy is a measure there of molecular disorder. So the second law of thermodynamics states that entropy can never decrease if not order is enforced by external influence. Also, some ideas from statistical mechanics has been included. So the energy function in Hubel networks is inspired by some models from statistical mechanics. Essentially, one model called the Ising model, and actually in this model have consist of discrete variables that in the statistical mechanics case represent magnetic movements moments of atomic spins. We can have two states, but the analogy here is clear. So also, you hopefully remember in Boltzmann machines, we have some processes clearly inspired by processes in metallurgy, where you heat up a material to very high temperature and then slowly cool it, and by that achieving that one can more easily reach an optimal state. And finally, very clearly in reinforcement learning, there are very, very strong inspiration and from control theory, operations analysis, and cybernetics. I mean, one could probably say that this is more than inspiration. I mean, in the same sense as math and statistics are important for a majority of the sub-areas of machine learning, control theory, cybernetics, and so on, are really, really fundamental to what one does in reinforcement learning. So by that, I want to end this lecture. Thanks for your attention. The next week of the course will be the final week. And essentially, we will focus on a repetition of assignments, related tasks as a rehearsal for the final exam. I think that will be the most important thing the last week. But also try to show you some larger examples of applications and some demos. Thank you.